Right, so let's maybe remember where we left off. Last time, so I was talking about these relatively precompact groups. Relatively precompact. Groups. Which, okay, so it was essentially from model theory, so automorphism groups. Zero categorical structure. Okay, and then well, I should probably mention now some closure properties of these groups, which I'm probably going to use. So maybe a couple. So they're closed under, so closed. I mean, the class of these groups, it is closed under, so they're several things of taking open subgroups. Okay. So if you have a relatively precompact group and you take an open subgroup, it is still so this is one. It's closed under taking quotients. Closed under taking products. I suppose this. I'm not sure I'm going to use this. Okay. And then one more thing. So considering open subgroups and permutation actions. So another way to define this. I mean, I defined it using these double cosets, but there is maybe a better and something that is used more often. Is that if you have an action of G on some set M, and then V is an open subgroup, then what happens is that so every G orbit splits finitely many. And so this is true for any permutation action of G. And conversely, if this thing is true for any permutation action, then the group is relatively precompact. It's actually quite easy to see that this definition is exactly the same as the double cosets, and it's just a different way to phrase this. But if you notice, this is a property which is sort of used all the time. All right. So another thing that we defined, last time was this. So we associated to every group like this. We associated this set U, which was left cosets of open subgroups. So this is a countable set on which the group G acts. And then, so we also did not take all open subgroups, but we somehow took from every conjugacy class of a subgroup, we took exactly one representative. And so the reason we did this, and it's not super important, but it makes sort of things technically easier, is that now for every, so okay, now the property that we get from this is that for some open subgroups is that if now V is an open subgroup of G, so if V is self-normalizing, so if it is equal to its normalizer, then there exists a unique element A in U, which is G of A. So you cannot, I mean, you cannot hope that every open subgroup is somehow the stabilizer of exactly unique single. GA is the stabilizer. GA is the stabilizer of A. Yeah, maybe so. This is a notation also. So GA such that GA. So you need some sort of condition like this, but at least so most open subgroups, I mean, the ones that do not have, that are not normalized by any elements outside the V. I mean, there is a unique point that corresponds to that. Okay, and so this is what you get by playing with this thing, taking the unique element of a conjugacy class. So, I mean, if you just write this down. All right. So now let me give you the definition. So I'm sort of going to abstractly try to explain some of the structures that these open open subgroups have, and then
So something so non-compact, pre-compact groups are not CLI, right?
yes,
They are never CLI.
they're never CLI. Okay, so maybe I should say one more thing. Okay, so CLI is complete left invariant metric. So if you say real complete compact and complete left invariant metric, this implies compact. So it is the same. Yeah. So it also locally compact and the real complete compact also implies compact for this reason. So this is maybe something which. All right. So let me also give you a couple more definition. So we said here this is U. So a subset D of U is called is definable. So the terminology comes from model theory, but it doesn't matter. I'm going to only define things using the permutation group action. So if its stabilizer is open, okay, so if GD, which is by definition is the set of G in G such that G times D is equal to Z. Yeah, so note that this is the set-wise stabilizer of the set. Okay, so it's allowed to permute the set, but it has to fix it. So this thing is open. Okay, yes. And then we also say that so D is locally finite if it intersects every orbit in a finite set. So for every A, so G. And also there is so the most important operation in all of this business is this what is called algebraic closure in model theory. So it can be defined in a very simple way. So the algebraic closure, well, let's say that A is finite. Okay, so take A to be a finite subset of U, finite, and the algebraic closure of A is just defined as the set of D in U, such that GA times D is finite. So this is all points which have a finite orbit under the set-wise stabilizer of A. So which is the same because A is finite. This is the same as taking the point-wise stabilizer of A, because the point-wise stabilizer has a finite index in the set-wise stabilizer because the set A is finite. And also this algebraic closure, so it has has the property that so if A is finite, then the algebraic closure of A is so what is it? Is definable. It is locally finite, and it is also it's also algebraically closed, I suppose. What does this mean? So, okay. So this algebraic closure you can define it for finite sets, but you can also define it for arbitrary sets. So if you have now an arbitrary set, I don't know, B, the subset of U, the algebraic closure of B is just defined as the union of the algebraic closures of all finite subsets. And then a set is algebraically closed. So algebraically closed, this means that the algebraic closure of B is equal to B. And of course, this algebraic closure operation, it is a real closure operation, so it's idempotent. Yeah? If you apply it twice, you get the same set.
It may not be finite.
It is not finite, yes. I mean, this is what I said. It is locally finite.
Yeah, but you defined it for finite A. That's right.
Yes. So I define it here for this is for an arbitrary set. I define it as the union of the algebraic closures of the finite subsets And then I think everything I said is correct. Okay. So now this is a lot of definitions, but so there is what else I want to say. Okay. So there's also partial order that we can define on finite subsets of U. So this is it's a quasi-order, I suppose. Quasi-order on finite subsets of U. Defined as follows. So A is less than B. So if I was forgetting which way I put it. Yes, if so, A is contained in the algebraic closure, okay, which is equivalent to GA times B is fine. This is well, it's a quasi-order. I mean, again, so all of the things that I say, that I mean, some of them are not completely obvious, and they use so everything uses in a very strong way that the group is Ryoka precompacted. I mean, if you have an arbitrary permutation group, I mean, all of these things are just not true. Okay, and not all of them are obvious. So if you actually try to sit down at home and try to like prove all of the things that I say, I mean, none of them are difficult, but I mean, some of them actually require proofs. And that they use in an essential way, I mean, sort of these properties.
So finite invariant sets are maximal of this one.
Yes. Yeah. I mean, so I'll say a few more things that should probably make you. Okay. Right. So we have this. This is a quasi-order, and then we can define an equivalence relation. So in particular, it's transitive. Yeah. So we have the equivalence relation that A is equivalent to B. Well, if A is less than B, and B is less than. Okay, and now, so I mean, I don't want to consider this order on all finite sets, so I want to consider, well, this is one maybe final thing. So if we have, so if a set D is locally finite, so it's like this here, yeah. So if it is locally finite, definable, and algebraically closed, locally finite, definable, and algebraically closed. Then in fact, there exists a single point A in U, which is equivalent, which has the same stabilizer. Okay, I suppose this is, I didn't define this very well. Such that the stabilizer of A is equal to the stabilizer. Okay. So this thing is called, it's called the canonical parameter, I think, for the definable set. Okay, so A in U, such that they have exactly the same stabilizer. And now, so what? Well, so I don't, as I said, I don't want to consider this order on all of the finite subsets. So, okay, and let's denote by. So we'll denote this thing by D in brackets. Okay. So if I have some definable set, which is again algebraically closed and locally finite, there's a unique element which has exactly the same stabilizer as this set, and I just denote it by brackets. Brackets. Okay, this is now just an element of it. Okay, and so now, okay, I want to define this. So curly A, this will be the set of this. So these canonical parameters, if you want, for finite subsets. So algebraic closures of finite subsets. So these are, I mean, I'll give examples. Okay, so I'm aware that this is a little bit abstract, and if you haven't seen this at all, it's not completely clear what these things correspond to. So I'll give examples in less than 5 minutes. I mean, in actually concrete structures, what this thing corresponds to. Okay, I'll give you maybe the only example that I know how to calculate this. But abstractly, they're somehow very useful for. Okay, so. Okay, so now just write a claim or a proposition, which again I'm not going to prove, and then I'll give an example. So what are the properties of this? So first of all, this A is a transversal for this equivalence. And transversal, this means that it intersects every equivalence class in exactly one point. Okay. So this is simply because, well, what do I want to say? That the algebraic closures of A, the algebraic closure of N, and these things are the same. I'm not sure what. Well, I should not write this. But I should write something which is correct. Yes. So A. This is
ACL is the name of ACL.
So A is equivalent to its this thing. So this is the reason why this is transversal. I mean, this intersects every equivalence class, and then it's easy to see that there is exactly one. Okay, so this in particular means that now when I restrict this order to respect A, this is a partial order. And then, so I'm going to use, I mean, there are two important properties. So, position. One is that this is a lattice. So lattice means that every two elements have a least upper bound and the greatest lower bound. Yes, correct. And then two, it is well founded. So well founded just means that there is no infinite decreasing chain. All right, so about one, I think I can comment. I can tell you what the operations are.
So back in the meaning of the models, is every set smaller than the empty set? Shouldn't be, right? Because it's not considered ACL of the empty set, but GA times the empty set. It's fine. So there's something wrong.
There is, okay. A second.
Should be the opposite.
Yes, it should be the opposite. Because A is in the algebraic closure of B, which means, well, I defined it that, yes, stabilizer of, that's right. Thanks. All right. All right, so what is the, so what are the next thing? So what is the least upper bound? So if you have A and B, so the least upper bound of A and B, so this is just the algebraic closure of the pair AB. The set of the two elements AB, and the least upper bound is the bracket of the algebraic closure of A intersected with the algebraic closure. So this is again, I mean, this is the intersection of two locally finite algebraically closed something, and then so it also has a bracket. And then what this is something that you check again using this compact nesting. All right, so now this, and maybe it was a little bit too much. So let me give you some examples, basically sort of the only examples which I understand. Yes. No, so for this, okay, I'll give a definition. So examples. Okay. And so the examples, well, I'll try to calculate this for some groups of, so automorphism group of M, where M is Aleph 0 category. So let me give you the definition. So we'll say that M has trivial algebraic closure. Or sometimes this is called as no algebraicity. This is another. The name of the same thing. If for every finite subset A of M, the algebraic closure of A is equal. So there are no elements which are algebraic over A. Again, we're using the same definition, or using the model theoretic definition if you want, which is equivalent. Okay, and so the second one is that this is a bit stranger if you haven't seen it. So we say that M also has a strange name, has weak elimination of imaginaries. Weak elimination. I don't want to explain the name, the reason for the name. It like this. So it's an abstract property actually. Well, again, it's a property of M. It's a property of the structure. If the following thing happens, so for every V open subgroup of G, there exists a tuple A from M, such that the following two things happen. So the stabilizer of the tuple A is a subgroup of B, and moreover, it has finite index. So A has finite index. Okay, so now let me give you examples of this, and then I'll tell you for these things what my set A is. Okay, so this should give you some idea of what's going on. So examples. So set without structures. This, so the linear order, the dense linear order has properties. So the random graph does things like triangle-free homogeneous graph, universal homogeneous graph.
Examples of which properties?
Of both properties simultaneously, because I'm going to use them in. Okay, so then what else? The universal partial or universal homogeneous partial order. So there are many more examples. Okay, so things which are maybe I'll tell you non-examples. For example, a vector space. If you look at the vector space over a finite field, I mean, this is a very nice L0 categorical structure, but it most certainly does not have trivial algebraic closure, right? Because if you have a finite subset, the algebraic closure is its linear span, which of course is not equal. Yeah? Because you have operations. Of course, every time you have operations, this operation, I mean, this thing cannot have the trivial algebraic closure. And so another one for the, if you want a counterexample for these imaginaries, so the simplest one is an equivalence relation. Okay, so you just have an equivalence relation. Okay, with infinitely many infinite classes. This is again, it's a very nice L0 categorical structure. Well, it does not have this property. Why? Because if I have, so this is my structure, right? So it has, this is one class, this is another class, and so on. And now what I want to find an open subgroup which does not have this property. Okay, so what is an open subgroup? I mean, I can just take the stabilizer of this class. Okay, so maybe I call this A here, and then I take a look at the class of A, and then I look at the stabilizer of the class of A. Okay, just the equivalence class. So this is clearly an open subgroup because, for example, it contains the stabilizer of this point. Okay, so it's an open subgroup. But now, if I have any tuple, I mean, certainly no tuple. The stabilizer of no tuple has finite index in this, right? Because if I stabilize 10 elements here, well, the index will still be infinite because it acts on the rest of the. Okay, so this is, I mean, basically the only reason that this thing fails is the existence of equivalence relations. Okay, I mean, it's basically the same. Okay, and so in this, so if I now have something which satisfies both of these properties, so if G is the automorphism of M, so M with no algebraic and with elimination of imaginaries, then this set A has a particularly simple form, so it's just equal to the finite subsets. With the order is just given by inclusion. Right, so this is a lattice. I mean, the least upper bound is given by the union, and the greatest lower bound is given by the intersection. And it's most certainly well founded. Like there's no infinite descending chain. Okay, so this is, I mean, this is the case that I understand. And this, all of the sort of the abstract nonsense before was to just give that there is, so this thing exists in a general situation. And well, it has at least some properties of this very nice, simple partial order. Okay, so far so good. So this is, if you want, this is the thing to think about, but again, I mean, it can be like significantly more complicated.
Imaginaries for this?
For this, yes. I mean, for example, an element here, which if I have the equivalence relation, the equivalence class will appear here. So if you want, so here, I mean, here I can calculate this set A. So what is in this case here? The set A, well, it will be all finite subsets of this. And moreover, I will also have all finite collections of equivalence classes. And then the order will be the appropriate order. The algebraic. So it will sort of have two levels. But it is still, and it will always be well founded. Okay? So even if somehow you try to have infinitely many levels and whatnot, I mean, the thing will always be well founded. And again, so if there are more equivalence relations, I mean, this thing can get pretty complicated. Okay.
So why do you need this elimination of the imaginaries?
Well, because otherwise here I have more elements. So this will always, these things finite subset, they'll always be there. But I have another one, for example, this equivalence class. Just the singleton of this equivalence class will be an element here. Because it will not be equivalent to any finite set of points, because it will not have the same. So I mean, there's a different way to view this set A if you are more group theoretically inclined. This is exactly, I mean, you can identify this with the collection of open subgroups of G that do not have supergroups in which there are finite index. Okay, so sort of maximal subgroups in which there is no finite index supergroup above. It's the same. But then I have troubles defining, I mean, the partial order is also usually defined as sort of inclusion up to finite index. But then I have trouble defining the lattice operations. I mean, especially one of them, which is the important one, which is this one. So this I don't really know how to define subgroups. So this is why I chose this maybe sort of roundabout definition. I mean, it's possible that this thing is not optimal. Okay, but
in the vector space, these are finite dimensional subspaces.
That's right. Yes. So in a vector space, the collection is just finite dimensional subspaces, and again ordered under inclusion. Okay. So now let's say what is sort of this good for. Okay, so well, to do this, I want to talk a little bit about unitary representations. What's the unitary representation? So we have a G, which is a group, and then topological properties. And then a unitary representation is just an action on a Hilbert space H. So this is a continuous action by unitary isometries. Okay, so my Hilbert spaces are complex. Yeah. Yes.
So in this implication, the algebraicity allows you to get rid of the ACL in your definition of A. And Y allows you to get rid of the bracket, is that correct?
Well, yes. I mean, well, so the weak elimination of imaginaries, what it allows you to do is that, I mean, that this is everything. Right? So these things will always be in A, but there may be other elements. Basically, all sorts of finite sets of imaginaries will be here.
But because the definition of curly A was the brackets of ACLs of things.
Yeah, but it was in U, I remember. It was not in M.
Oh, yeah.
So there is this U, which I preliminarily defined, I mean, to actually contain all imaginaries are there. And so this weak elimination of imaginaries tells you that M up to finite sets essentially captures the U, which I put right. I mean, this is, if you think for a second, this is exactly what this tells you. Okay, so again, a unitary representation is just a continuous action by unitary isometries on a Hilbert space. Okay, so this is a complex. Okay, so a typical, I mean, if you have a permutation group of G, N is a permutation group. As we saw last time, I mean, you have sort of an obvious representation of L2 of M. Yeah, so this is just all square summable functions on the set N, and you just act by shift. Okay, and so now the whole point of all of this, I mean, what this mini course is about is that when G is non-Archimedean Rho-Capri pre-compact, then actually these representations, they exhaust everything. Okay? There are no other unitary representations. So let me make a precise statement. So it's a theorem which I put a long time ago. Obviously, it doesn't. Right. So again, so we assume that G is non-Archimedean Rho-Capri pre-compact. And then like this, then every unitary representation of G So is a sub-representation of a direct sum of copies of L2 of it. So the theorem is actually more precise. I mean, it tells you about irreducible representations and so on. But this is really the only form which I found useful, which actually allows you to prove it. It's very easy to state. So you have this set U, which this universal thing, which I defined. You have this representation, which is, well, okay, just the permutation representation of this. Then you take a lot of copies of this, take direct sum, and then every representation will appear somewhere as a sub-representation of this U. Is this U which I defined in the beginning, which was, you remember, this all left cosets of open subgroups. Not all open subgroups, but you know, if you take all, it also works because it will only become bigger. So this is it's a pretty strong statement, right? Because so unitary representation is an abstract thing, and then it tells you that all of them you can somehow see them in this permutation, universal permutation. Well, the set A, the way I defined it, I mean, this really captures all of the important properties, well, at least for some things of this representation. Okay, so I'll explain this in a second. All right, so now let me well, prove a consequence of this, which I'm going to use. So here is a proposition. For the proposition, I think we have to define something. So we have some unity representation. So suppose H. So let's see, E on H is a unity representation, and then A is an element of A. Okay, this A, which remember, so the U and the A are just abstract things which are just defined from G. Okay, there's no other information. Okay. So take some A in A. Now I'm going to define H. A is the set of psi in H that GA psi finite. So these are all vectors that have a finite orbit under the stabilizer of this A. This is some open space. This is a subspace vector, which a priori could be zero. Yeah. Often it is.
This representation L2 of U is not
Oh, this is most certainly not irreducible. Yes. I mean, this U has a lot of orbits. So in particular, I mean, if you just split by orbits, you get sub-representations. But you also can get more. I mean, even if you have a single orbit, of course, it can also split. But this also allows me to not talk about irreducible representations. All right. So this is, I mean, it's not hard to see that this is actually a and the thing that I defined here is closed under addition. Right? If I have psi and eta, which have finite orbits, then psi plus eta will also have a finite orbit. So, I mean, so this finite just means that the stabilizer of this has finite index, and then if I take the intersection of two subgroups of finite index, still has finite index. Okay, so so now here's the proposition. So now if G at from H is an arbitrary unitary representation, well, and A, B are elements of A, then the following thing happens. Then HA is orthogonal to HB over H of the least upper bound of A and B. Okay, so maybe I should define what this is. So there's sort of one thing which is obvious. I mean, this thing respects the order. Okay, so if I have that A is less than B, this implies that H of A is included. Okay. So I sort of get a lattice homomorphism from A into these subspaces. Okay, subspaces of H.
Because GB contains G. Because GB is contained in GA.
Yes. Well, GB. Oh yes, for elements of A, the GB is not contained. This is not, but there's a finite index. So there's a finite index subgroup of one which is contained in the other, and this is enough because I have this finite. It is not true. I mean, imagine just for, say, for S infinity. I mean, if I have a stabilizer of 5 things and the stabilizer of 6 things, it is not true that the setwise stabilizer of the 6 things is contained in the setwise stabilizer. So what does this mean? So again, so this is a subspace above this and this. So this just means that this is orthogonal. B. I mean, it's the most natural thing, right? So this is a subspace both here and here. So I take the orthogonal complement of this in this, which is this thing. Then I also take the orthogonal complement of this space in this space, and I claim that the two things are orthogonal. So this just means that basically the direct sum of HA and H, I mean, the sum of HA and HB splits into direct sum of 3 things. So this one, and then the orthogonal complement here, and the orthogonal complement there. So things are sort of as independent as they can. Okay. So this just follows quite directly from the theorem. So maybe let me do it. Okay, so this property, okay, so this I'm not going to check, but just believe me. So the conclusion, stable under direct sums and subrepresentations. Okay, meaning that these operations, I mean the A, I mean taking this A thing, this commutes with subrepresentations and direct sums. So it's basically what I'm saying is that by the theorem, it's enough to just check the statement for this particular representation. So enough. For H. So I told you that this theorem simplifies life a lot because it reduces an arbitrary representation to this one, which we understand reasonably well. Okay, so now, well, now in this representation, I really want to understand what this HA is. Okay, this is very easy. So now HA is just O F in L2 of U, such that the support of F is contained in the algebraic closure domain. So this is all functions whose support, I mean, so the places where they're not 0 is contained in this. Okay, so why is this true? Well, okay, so let me do maybe let me do both directions. So let's do the first one. So okay, so HA was defined as the closure of these things there. So the thing on the right is closed. So it is enough to check that these things are okay. So take psi in H on L2 of U, such that G8 psi is fine. Okay, so now suppose that oh, maybe F. I should call it F. Okay, F. So now suppose that this thing does not hold. Okay. So this is finite. So this means in particular that the stabilizer of F. So there exists V, which is a subgroup of finite index. So finite, which stabilizes F. Now suppose that this support is not contained here. Okay, so then this means that there exists a B, which is not in the algebraic closure of A, such that F of B is non-zero. But then you see, I mean, the V orbit of B is infinite. So this thing is infinite. And again, so we have a function which is non-zero somewhere. By V invariance, I mean, it is fixed by this V, so it has to have the same constant value on the same, I mean, on the whole orbit. And then this cannot happen, yeah, because it's an L2 function again. So it's the same trick from last time. So if you have an L2 function, it cannot take a constant value on infinite side. Okay, so that's, well, that's it, I suppose. Okay, so this is one direction. And then the other direction is also easy. So let's do it. Well, so the other direction is whatever. So what is there to say? So if you have so this algebraic closure array, I mean, remember, maybe it is not finite, but it is locally finite, so I can write it as an increasing union of AI, such that each AI is finite, and A invariant. And then what happens is that now if F is the support of F is contained in the algebraic closure array, well, this implies that F times the characteristic function of AI converges to F in norm. That's simply because, I mean, these sets, they dissolve the algebraic closure. So if I just cut the support to some finite set and I take the limit, it will converge to F. And these things, I mean, because these sets are invariant, these things have finite. Okay. And then there I took the closure, so the limit is also. But there's, there's nothing to the whole business. All right. So, but once you have this, you can actually, now, even though it's pretty easy, there are some interesting consequences, so I'm going to explain maybe some of them now, and. And then maybe okay. So, and I suppose it is clear why this thing holds, right? Because if you remember how this thing is defined, okay, so the A B was just the algebraic closure of A intersect closure. B. So, right? To say. So HA are the functions whose support is the algebraic closure of A. These are the functions whose support is the algebraic closure of B, and these functions are the ones whose support is the intersection. Okay, so this thing obviously holds. All right. All right. So here is there's an application. So this is sort of a version of the Finetti's theorem. So this is in a paper with Coulomb. And so now, as I said, so the only situation in which I really understand things is when the set A is this finite subset. So I'm going to make these two assumptions. So let's suppose that now M is Aleph zero categorical, so no algebraicity. What else? So weak elimination of imaginaries, and I also want to suppose that it is transitive. So this the last one is not really necessary. It's just to make the conclusion simple. Okay. So transitive just means that the action of the automorphism group on M is transitive.
Conclusion will be when M is natural numbers with the identity.
So the classical version of the Finetti's theorem would be when this M is in the empty language, so the group is the full symmetrical. Yeah, but it also applies in all of these things that I listed before. Okay, and now let's see. So now let's look at G is the automorphism. Okay? And look at G. Acts on this compact space. So 0, 1, the M. So this is the same situation as and it was explaining yesterday. Yeah? So we have this action this X here, and then we have some invariant measure. Okay, so mu is G invariant, and I want also to assume it is ergodic. Okay. So the ergodicity assumption, this avoids these mixtures of IIDs and whatnot. So just now there are no mixtures. Everything will just be IID. So the conclusion is that these things are IID. So let me make the imprecise. So there exists. So now the conclusion. Then there exists a lambda, which is a measure 0, 1. Such that mu is an infinite product of the numbers. Okay. So I mean, this measure is obviously invariant. Right? You can take any measure on 0, 1, and then you just take the product measure. It is obviously invariant under all permutations. In particular, it is invariant under the oligomorphic group of M. So this tells you that well, these are the only ones. Okay, under these very strong assumptions. On the well, it's still they apply in for a lot of situations, but certainly not in all situations. But, okay, so if you have this, then so this is yeah. So if you take so for the full symmetric group, which is I suppose the weakest version of the theorem, because then you know if you have the full symmetric group, so you get the strongest invariance, right? I mean, the bigger the group, the weaker the theorem. So if you want to get stronger theorem, you make the group smaller because the assumption is weaker. All right. So for when G is just the full symmetric group, so this is the kinetics theorem. When G is the automorphism group of Q, so the theorem is due to Riemann-Zevsky, not exactly under this formulation, but yeah. In an equivalent formulation. And then, well, of course, in the general case. All right, so let me prove.
Sorry, lambda is what? Then there's
It's a measure. Lambda is just an arbitrary measure on the on 0, 1.
0, 1, 0, 1. Okay.
Okay, so an alternative formulation, if you want, which maybe is the one that I'll prove, is that if you have so you have random variables which are indexed by the structure M, whose distribution is invariant under the automorphism group of M, or then they have to be independent. Okay, so this is big. I mean, and you assume ergodicity, then they have to be independent.
So you M is
Yes, thank you. Well, I suppose isn't this implied somewhere? Like no algebraicity. I'm pretty sure my definition of no algebraicity implies it is infinite. Because I'm not actually using it in the proof, so but yeah, it has to be. All right, so let's prove this. We said the proof is very simple. Okay, we need a unitary representation to apply all of this machine. So every time you have a measure preserving action, of course you have what is called the Koopman representation. So we have the representation L2. Which is the usual thing, right? So it acts. The group just acts by shift on L2 functions. Okay, so now let's see. So this representation, it always has a fixed point. Okay, so there is the constant 1 function. I mean, this is an element of F2, and of course it is fixed. Right? You have a constant function and you shift it. Okay, so this is always a fixed function. And now the ergodicity assumption biases that this is the only fixed point. So the orthogonal complement of 1 has no fixed point. Okay, so let's so the orthogonal complement is denoted by L to 0. So this is the set of all f of integral 0. F in F. Okay. So this is just the orthogonal complement of the constant function. Okay, so the ergodicity assumptions, as I said, so it biases. So it biases that there are no fixed points here. Okay, so G has no vectors in this is one. Now the second thing, so maybe I'll denote this by H so that I can use my notation. Okay. Okay, now so let's see what we have to want to prove. We want to prove that these things are independent. So let's take two finite, so A and B are finite subsets of them. And let's denote by FA is the sigma field or sigma algebra. Sigma algebra generated by psi A. So what is psi A? Psi A is just the projection on the A point. Okay, so psi A is a function from 0, 1 to the m. 0, 1 is just the projection on the coordinate a. Right? And then so we have all of these. These are our random variables, are these projections, and we want to show that they're all independent. For a. Right, so now I take the random variables, I mean the projections on the a coordinates, and I just take the sigma algebra generated by this. And then similarly I do as this. Okay, so now let's denote by L 02 A. Oh, this will just be all things which are in here. So this is OF in L, which are measurable with respect to this sigma. Okay, so the F is A measure. Okay, and similarly for the other. Okay, so now let's remember what the goal is. So our goal is to show that these two sigma algebras are independent, and this is enough, right? If you want to show that we have a collection of random variables which are independent, it's certainly enough to take any finite set and then disjoint finite set, look at them, and show that the sigma algebras generated are independent.
A and B are disjoint.
A and B, yes, thank you. A and B are disjoint. Okay. Right. So this is what we need. Okay, so now let's see what the so now let's see what the. I mean, remember our set A was just the finite subsets of M. Okay, so particularly, I mean, A and B, I can consider them as elements of A. And well, it's quite easy to see that so HA is actually equal to this L to 0, and HB is equal to this one. HA was the things which had the finite orbit under the setwise stabilizer of A. And this is the same as the things which are measurable with respect to this. Okay, and then you also have this. Okay, so now we can apply our theorem, which tells us that HA is orthogonal to HB over the intersection. I mean H of. But the intersection is the empty set. Yeah? And then, well, H of the empty set, these are exactly the G invariant vectors.
So this is HA intersect on 0 to 0.
Yes. Well, no, the H, I think. So let me just for a second. Where was the definition of H? So H is L to 0. So that's why this is. This is okay. The weight is written. Okay. So now here this A intersected with B is the empty set. And of course, the stabilizer of the empty set is the whole group G. But remember, there was nothing which was G invariant. I mean, this was the ergodicity assumption. There's nothing which is G invariant. I mean, this thing is actually 0. Okay. So we just get that HA and HB are orthogonal. Well, so this is the same. I mean, this is sort of basic probability theory. So two sigma fields are independent if and only if the L2 functions from one and the L2 functions from the other are orthogonal. And so that's well. So this finishes. Yeah, this finishes.
So this gives you that they're independent. What about identical distribution? I guess it's probably true.
Okay, so this gives you they're independent. So why are they IID? Because I have this assumption. So in particular, I have an element G that sends psi A to psi B. So I mean, they must have the same distribution because this preserves the distribution. Thanks. Right. So otherwise, if you don't have this transitivity assumption, I didn't use it. Yeah. So you just get that they're independent. But if you also have transitive, then they have to be IIDs.
Did you want to use Neumann lemma?
Not here. I'm pretty sure. So it is used in the things that in these properties of A and so on. It is definitely used there. But well,
You used it yesterday.
yeah, I used it yesterday for ergodicity. But okay, so let me just say one more thing, and then I'll stop. So it is also to relate. Well, so next time there will be quasi-invariant measures in honor of Anush. And I also wanted to say something about simplices. So there is another thing which follows from sort of a side thing, which again follows from this representation theory business. So this is something that we proved with David Evans, is that some non-Archimedean real compact groups have property T. So you can also remove non-Archimedean, remove this, and then you get a much harder theorem, which is due to Tomas Garcia. So this is also true. I mean, just all real compact groups, they just get the property T. But so what is the, well, so why am I saying this? So this implies in particular that so every time you have a group like this, which acts on a compact space, then you look at the simplex of invariant measures. So it implies, by result of cluster advice, that it's always a Bauer simplex. So the ergodic measures are always closed. So it's a very special situation, but it holds for all of these groups. So here, how is this illustrated in this example? So look, so what is here? What is the Bauer simplex? So the extreme points are just the measures on 0, 1. Right? So an extreme point is given by a measure on the set 0, 1. And then all measures are just the measures on 0, 1, right? Just because, I mean, this is what the Bauer simplex is. Bauer simplex is just the same thing as the simplex of measures on extreme points, which is a compact set. So this is how you see this thing in this situation, the finite situation here, but it's a completely general fact. That's all that every time you have a group like this which acts on a compact space, the invariant, I mean, the ergodic measures are always closed. And this follows from this.
Like this,
Very openly compact, which is okay. So I think this is a good time to stop.
I didn't read the link between your theorem with the Colonel, and when you say there's a link with the definity theorem and especially with the Latevsky theorem in the case of automorphism of Q.
Yes. So what is the Definitis theorem? So Definitis theorem is the what when you just take G is the full symmetric group of. It's one possible statement of this theorem, right? That if you have this exchangeable random variables, which just means exchangeable, just means that they're invariant under the permutation. I mean, distribution is invariant under the permutation group, then they have to be independent. You assume that the measure is ergodic. So this is definitive. And Lyon-Rzhevsky is the same statement. It is not the regular Lyon-Rzhevsky theorem about zero categorical structure. It's a different theorem of Lyon-Rzhevsky. It has many theorems. So he's a very prolific Polish mathematician who worked in many areas. One of them is probability theory. So he proved this exchangeability thing for random variables which are indexed by the natural numbers, not by Q. But then the assumption is that if you have two tuples, say A and B, which are ordered in the same way, then they have the same distribution, the corresponding tuples of random variables, and then they have to be independent. And then, well, you can get it using basically Frey-Set theory. You can get from N to Q and then apply this. So this is the. Okay, maybe I should. I wanted to say one more thing, which I forgot. But it's okay. So are there more questions?
So basically, there's nothing special about 0, 1 here, right?
Oh, there's nothing. It's about any set. No, you don't need compact. It doesn't matter, right? Because
Well, if you
yeah, but the measures they do not depend on topology. So I can just put a compact topology.
okay.
It's irrelevant.
But if you want to say that you realize a particular Bauer simplex, then it is enough to put a family of compact metric spaces to realize all Bauer simplices as simplices of invariant metrics for those actions. Any more questions? If not, then to jest cały czas przegła to mowa na górze?